Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on real-life linear programming problems. In our previous lesson, we introduced a step system as an easy way to work through linear programming problems to find optimal solutions. We have also practiced with several examples of linear programming problems. Today will be our last lesson on this topic. So, we will resolve a challenging question together. Please ensure you have a pencil, graph paper, and a ruler so that you may take notes as we work through this task together. Let us now introduce a problem. The Ahadu company produces two models of radios. Model A requires 20 minutes of work on assembly line 1 and 10 minutes of work on assembly line 2. Model B requires 10 minutes of work on assembly line 1 and 15 minutes of work on assembly line 2. At most, 22 hours of assembly time is available on line 1 and 25 hours of assembly time on line 2 per week. It is anticipated that the Ahadu company will realize a profit of 10 Birr on model A and 14 Birr on model B. Students, now that we have all the information needed to solve this problem, can you follow the steps we introduced last lesson to determine how many radios of each model should be produced each week to maximize profit? We will take a few extra minutes to allow you to process all the data. Please get started.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, everyone. This was not an easy question. Hopefully, you used the guidelines of the 6-step process to solve this problem successfully. Let us go through the steps together and compare results. Our first step is to summarize the relevant information in table form. We can do this in a number of ways, but this example provides the most accurate description of our parameters. Note that because the production of the radios is measured in minutes, we must convert the total assembly line time into that form. Thus, on assembly line 1, the total available time is 1,320 minutes, and the total available time on line 2 is 1,500 minutes. Our second step is to form a mathematical model of the problem by introducing decision variables and expressing the objective function and the constraints of these variables. We can use variable x to represent the number of Model A radios. We can use variable y to represent the number of Model B radios. Because our objective is to maximize the profit on the production of both radios, our objective function appears as P is equal to 10x plus 14y. This is subject to 3 inequalities. The first inequality is one we have become accustomed to seeing in linear programming problems. X is equal to or greater than 0, and y is equal to or greater than 0. The second inequality is 20x plus 10y is equal to or less than 1,320. This represents the quantities of Model A and B being assembled on line 1. The third inequality is 10x plus 15y is equal to or less than 1,500. This represents the quantities of Model A and B being assembled on line 2. It is now time to graph the feasible region and find the corner points. Since we are searching for the maximum value, the region will be to the left of the lines on the graph. If you have calculated your vertices correctly, Your graph should appear as you see it here. We can see from the graph that the intersecting point is at 2484. Therefore, there are 3 vertices we can use to test for the maximum point. Step 4 is to create another table, adding a column for the values of the vertices and another column which substitutes these values into the objective function. We are now able to determine the optimal value from the table. The correct answer is the point at 2484. Our last step in the process is to interpret the optimal solution in terms of the real-life problem. Students, what is the importance of this step? How can we present the solution to this problem in real-life terms? Take a few minutes to do so now.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Did you find this question difficult? It is one thing to solve a question for its mathematical values, but it is another to interpret the results. The purpose of step 6 in our process is to simplify our answer into something that we can understand and that applies to the real-world scenario we are examining in our problem. Our objective in this problem was to maximize the profit of P. The maximum production possible for radio models A and B are 24 radios on assembly line 1 and 84 radios on line 2 for a total profit of 1,416 Birr. It is very important that you relate your results to the problems presented in the first step of the process. I will leave you with one last exercise to consider before we finish today. You may work with a partner to complete this activity once the lesson is over. The officers of a high school senior class are planning to rent buses and vans for a class trip. Each bus can transport 36 students, requires 4 supervisors, and costs 1,000 Birr to rent. Each van can transport 6 students, requires only 1 supervisor, and costs 150 Birr to rent. The officers must plan to accommodate at least 420 students. Since only 48 parents have volunteered to serve as supervisors, this is the maximum available for the trip. How many vehicles of each type should the officers rent in order to minimize the transportation costs? What is the minimum transportation cost? Students, this concludes our lesson on linear programming. Today, we have reviewed the steps in resolving linear programming problems and examined a complex example while making use of the 6-step process. I hope you have found this useful. Until next time, thank you, teacher. Thank you, students.